Excuse me, David.
Hi, Martha. Come on in.
Do you have time to help me with a problem I'm having?
I will if I can.
Oh, great. I am confused about cancellation.
I think I might be of a little help on that. What's the problem?
First of all, I don't see any reason for it. I get good answers without it, so why bother?
Start there. The purpose of cancellation is to make working problems quicker and easier. You don't have any trouble reducing answers to the lowest terms, do you? Let's try this. 3/8 times 2/9. Solve this for me, will you?
Okay.
Now do what you normally do.
All right. 3/8 times 2/9 equals 6 over 72. Now, this will probably reduce, so let's see. 2 goes into both the numerator and the denominator. Maybe 3 does, yeah. Maybe 6. Yeah, 6 will go into it. 6 goes into 6 once, and into 72 12 times. 1/12 is the answer.
Okay, now that's the right answer, but it took a while to get that, didn't it? First you use this number, then you use that number before you found the right factor. Okay, I'm going to work this problem again using cancellation. Now, I think you'll find it's a lot easier. Just think of cancellation as reducing the problem before you solve it.
What do you mean?
Okay, this is what I do. 3 goes into 3 once. 3 goes into 9 3 times. 2 will go into 2 once. 2 will go into 8 4 times. Okay so far? If I multiply this out, I'll come out with 1/12 directly.
I don't quite understand that.
What did you divide by?
6.
Took you a while to find that 6, didn't it? What did I divide by?
Well, you divided 2 and 8 by 2, and then 3 and 9 by 3.
I divided by 2 and 3. Is that what you're telling me?
Yes, I guess so.
Okay, well, I'll make sure I know. I'm dividing by 2 and 3. I don't want to talk you into this.
Yes.
Yes, what?
You're dividing by 2 and then by 3.
Okay. How long did it take you to finally, what was the number you finally come up with?
6.
6.
Oh, 2 and 3 are 6. Or, I mean, 2 times 3 equals 6. That's what you were trying to show me, isn't it?
That's it. You divided by 6 after the problem. I divided by 6 before. You ready for some operating?
Operating?
Sure. Multiplication and division are arithmetic operations. So, let's operate. Okay, let's try 3/4 times 8/9. Now, right away, I see that the 3 and the 9 can be divided by 3. So I have a common factor for one denominator and one numerator.
Okay, I see that.
Okay, this is what I do. 3 into 3 goes once. Put a little 1 up there to indicate that. 3 goes into 9 3 times. Put 3 down there to indicate that. Do you see a common factor for the other denominator, other numerator?
4.
Okay. Show me the mechanics on that.
Okay. 4 goes into 4 once. Cross out the 4 and put 1. 4 goes into 8 twice. Cross out the 8 and put 2.
Okay, what do you have left?
1 over 1 times 2 over 3 equals 2/3.
Make more sense to you now?
I think so. Let me try one by myself.
Okay. Let's try 2/3 times 9/16. See what you do with that.
Okay. Now, I'm looking for a common factor that's going to go into both the numerator and the denominator, right?
That's right.
So 2 goes into 2 and 16.
Good. Now go on with that.
Okay. 2 goes into 2 once and into 16 8 times.
Okay, how about the other one?
3 goes into 3 and 9.
Okay, go on with that.
So 3 goes into 3 once, 3 goes into 9 3 times.
Okay, now what do you have left?
1 over 1 times 3 over 8 equals 3/8.
I think you got it. I think you really got it.
Maybe.
Just think of cancellation as a way of reducing the problem to its lowest terms before you multiply. By doing that, you keep the terms small so you can work them in your mind.
Okay, I see that.
Now, cancellation can also be used in dividing fractions. Okay, once you invert the divisor, sometimes you can cancel. If you can cancel, you can keep the numbers small, less margin for error. me show you what I mean. 3 1/8 divided by 5/8. Okay, operate.
3 times 8 equals 24, plus 1 equals 25/8 times 8 over 5. Now, 5 goes into 5 once. 5 goes into 25 5 times. The 8's just cancel out. So we get 5 over 1 times 1 over 1 equals 5 over 1. Or just plain 5.
By Jove, I think she's got it. See how cancellation can help you?
Well, I'm a lot less confused now. Thanks again for your help.
Hey, you're welcome.
Hello, Steve Weiss here again. You should know by now that cancellation is used in multiplication of fractions to simplify the calculation. It is rather like reducing your answer before you have an answer. It works by finding a common factor for any of the numerators and denominators and dividing by these factors. Here's an example. 3/4 times 8/15. 3 is a factor of 3 and 15. And both 4 and 8 can be divided by 4. Therefore, the fraction would become 2/5. In division of fractions, after the problem has been changed to a multiplication problem, use cancellation if you can. Here is an example of how that application is used. 3/8 divided by 3/4 is equal to 3/8 times 4/3. And by cancellation, we reach the answer of 1/2. Well, that's enough about cancellation for now. Let's get back and see what's happening.
Okay, folks, if you're all ready, let's get started, okay? The refreshments tonight were furnished by Nancy and Harriet. Take a bow. All right, if you're all ready to pay attention, let's talk a little bit about cancellation. Now, first, are there any questions or comments about the cancellation problems that we had last week?
Well, I've noticed that when you have a problem that cancels, by switching the numerators, you end up with 2 new fractions that'll give you the same answer as the 2 original.
Well, why don't you come up here and show us that, Todd?
Well, all right. Okay, let's say we start with, 3/8 times 4/9. Now, neither of these fractions will reduce, but they will cancel. So if I switch the numerators and rewrite it as 4/8 times 3/9, then both will reduce.
Well, sure, 3/9 is 1/3 and 4/8 is 1/2. So what?
So what? 1/2 times 1/3 equals 1/6. And that is the same answer that you'd have as if you'd multiplied 3/8 times 4/9 in the first place.
So why not just multiply them in the first place?
Well, I would have, but I like to know what's happening. I mean, this is a whole new process for me.
Me too. I never noticed that before.
Well, do another one, please.
Well, all right. Let's do, say, 3/5 times 5/6.
Well, are you telling me that the answer to that is the same as 1/2 times 1?
Yep.
Wait a minute. You just lost me. You went too fast.
Okay, let me see if I can show you. Okay, thanks, Todd. What Sue saw immediately by trading denominators, she could get 3/6, and 3/6 is the same thing as 1/2. She also saw that 5 over 5 was equal to 1, and 1/2 times 1 equals 1/2. Everybody got it? Okay, good, good. Sometimes you can solve a very difficult problem in your head if you can easily recognize a different expression that means the same thing.
Yeah, David told me the same thing. If you can't figure out the problem as it is, then try and find an equivalent expression that you do understand, and then you will be able to figure it out.
Why does it work?
Anybody want to handle that?
Intuition, maybe.
Got to do better than that. Why does it work, Frank?
Well, let me try to explain. Multiplication of fractions is really a study of both multiplication and division at the same time. You see, the numbers above the line are divided by the numbers below the line, all right? Now, because of an important principle in mathematics, the sequence in which you perform these operations does not affect the outcome. So it would be like writing both numerators and denominators above and below the same line.
What do you mean?
Well, okay, let's see. Take 3/8 and 2/9. Now, do all of you see that this is the same thing if I write it like this? Huh? Okay, now 3 times 2 is the same thing as 2 times 3, isn't it?
Right.
Huh? All right, so then surely I can rewrite this like this because I haven't changed the value of the quantity above the line.
Hey,
Okay?
look at that. Now it says 2/8 times 3/9. Those aren't the fractions we started with, but they'll give us the same answer as the original fraction.
That's right. That's right. Let me just finish this computation. 2/8 is 1/4, 3/9 is 1/3. 1 times 1 is 1, 3 times 4 is 12, and there's your answer, 1/12.
Oh, okay.
Okay, everybody see that? All right, now what happens when we go back the other way? Now, would anybody argue with this statement? No? Okay, now what happens when I leave one of the numbers out? Say 4 times something equals 12. Do you all know what operation we perform in order to find the value of something?
You divide 12 by 4.
12 divided by 4 equals something. All right, in this case, that's 3. Now, shouldn't that same thing be true with fractions?
Well, it is true with fractions, right?
Well, let's just see if it is. 1/4 times something equals 1/12.
So I suppose we just invert the divisor and multiply.
Well, what if we don't this time? What if we just divide right straight across the same way we multiply?
Heck yeah. 1 divided by 1 is 1. 12 divided by 4 is 3, and that's amazing. Does that work every time?
Well, sorta.
What do you mean, sorta?
Well, you always get an answer, but you may not be able to understand it.
Do another one that you can understand.
Okay, what's 4/9 divided by 2/3?
Oh, well, 2/3. That one jumps right out at you. Now, you're just picking out examples at work, aren't you? Because if they all did this, there wouldn't be any need for the inversion.
Okay, Bill, you got me. All right, now divide this one right straight across then.
3 divided by 1, what's that?
3, or maybe 3/1.
And 4 divided by 3 is 4/3.
Okay, right, there's your answer. 3/1 divided by 4/3.
Hey, wait a minute. That's not an answer at all. It's just a problem written in a different way.
Well, it really did work out, Bill. It's just that you don't recognize this answer as a compound fraction, 3/1 divided by 4/3. We're used to having our answers in simpler terms.
I'd like my problems in simpler terms.
Well, is that the right answer or not?
Well, it's one answer. Let's see if we can find something that makes some sense out of this. Now, this may be a pretty far-fetched example, but what if you were in a church and for every 3 people you had 4/3 songbooks? Now, ignore the weird numbers there, but does this begin to sound like anything you've ever heard before?
Fraction family?
A fraction family, right. Can you find a family of equivalent fractions for this compound fraction?
Sure, but it's strange.
Well, let's just try it just for fun, okay? 3/1 divided by 4/3 equals 6/1 divided by 8/3 equals 9/1 divided by 12/3 equals 12/1.
Wait a minute, this could go on forever and I wouldn't see anything I recognize.
Maybe not. Look at the 3rd member of that family.
Yeah. So both of those numbers reduce down to become a simple fraction.
9/3,
Nine,
a simple
9 and
fraction.
4.
9/4. Now, isn't that the answer you were trying to find in the first place?
So it was.
All right, now let me get this straight. What you're saying is if we have the numbers in a fraction can evenly divide across, then you simply divide straight across. But if they don't evenly divide, you can still do it, but you won't understand the answer until you can do something to it to make the parts of it into whole numbers.
That's it.
I don't even know what I just said. Could you do that problem again this time, Frank? Only run a fraction family that uses the original fraction.
Okay, here's the problem we started with in the first place. So let's write it as a compound fraction. 3/4 divided by 1/3, okay? That equals 6 over 4 divided by 2 over 3 equals 9 over 4 divided by 3 over 3 equals 12
So it comes out even again as the third member of the family.
Now, there must be something about these numbers that makes it work out like that at the third member.
Well, whatever happened to invert the divisor and multiply?
Now, why does that system work, Bill?
Oh, you guys and your whys. Listen, just give me a rule and I will follow it faithfully.
Martha, there are rules for everything, but you couldn't remember all of them. Sooner or later, you have to start thinking in numbers.
Isn't there an easier way to make math more difficult?
Well, there's an easier way to make it easier. Let's take a break before the next part of the session, okay? And when we come back, I want to see if I can explain to Sue why it works out like this on the third member of the family. She hasn't quite yet got the whole story.
He's not the only one.
Here is another thing you should remember about cancellation. It works because in a problem involving only multiplication and division, the sequence in which you do these operations doesn't matter. For instance, here are 3 ways to solve a multiplication of fraction problem. In this one, you multiply straight across and reduce your answer. This example shows that you can cancel or reduce before you multiply. And here, you trade numerators and simplify the expression. Are you surprised that the idea of fraction families we spent so much time with in the section on addition and subtraction still has some importance all the way to division? Stay tuned for more about the division of fractions.
Counting sticks seems like kid stuff, huh? Well, don't you be too sure. Today, we are going to be moving up in our thinking.
From where to where?
Well, Martha had the right word a little while ago. She said intuition.
What's that mean?
Well, Martha, it's your word. What does it mean?
Well, it means when you know something just because you know something. I mean, there may be reasons for it, but you just don't bother to find out why.
Now, do you think that intuition is the same thing as thinking intuitively?
I don't use either of those terms, Frank.
The terms or the process?
Neither one.
Frank's trying to make a point. What is the point, Frank?
Thank you, Sue. The point is, I believe that intuition is sort of like magic. It's a flash of understanding when you know something to be true, even though you don't know why.
Like in the cartoons when you see that little light bulb above Donald Duck's head?
Yeah.
That's perfect. That's a perfect example, right? You see the light, right? But what I want to encourage you to do for the next few minutes is to think intuitively.
And how is it different?
Well, they're related, but I think that thinking is a way to process intuition.
Frank, what does all this have to do with that bunch of sticks?
All right. Okay, Bill. Now, I'm going to show you something that your intuition will know the answer to and know it to be true, and you won't even have to figure it out. You'll just know, okay?
Yeah, sure.
All right, I want you all to take a look at this. Okay. All right, Sue, how many sticks did you see?
12.
Did anybody see anything else?
Well, I saw 6 and 6.
Aha. Is everyone listening carefully? Sue saw 12 sticks. Bill saw 6 and 6. Then did you add those 2 6s together?
No, I just knew. You know, there are 12.
You just knew intuitively. Huh?
You
You see how easy it is to accept 12 as 1 pile or as 2 piles of 6 each? You just know, right? All right. Now, what does this have to do with mathematics?
Well, 12 divided by 2 is 6, and divided by 1 is 12.
Well, is this a division problem, then?
Yeah.
In a way,
All right, well, let me ask you some questions then, okay? If I have 12 things put into 12 piles, how many in each pile?
1,
12 things put into 6 piles, how many piles?
2,
Into 4 piles.
3,
Into 3 piles.
4,
Into 2 piles.
6.
12 things into 1 pile is how many?
Hell.
12 things put into 1/2 pile. What's wrong?
There's no such thing as a half a pile.
Yeah, but you could break the sticks.
Oh, well, is that the same thing?
Sure, 24 halves. 12 divided by 1/2 is 24.
Well, that's the right answer, but it's the pieces that are half as big, not the pile.
But that is the right answer, though. 12 divided by 1/2 is 24. Who's right?
You both are. Now, what you have done, Sue, is demonstrate one meaning of 12 divided by 1/2. There are 24 halves in 12. But you could have showed us that on a number line as well as breaking up all these sticks.
Well, then all you have to do is cut the markers in half, and then you have twice as many.
Now that is priceless, Martha.
What did she say?
She said you do not make one pile half as big. You make one pile with twice as many pieces in it called halves. Now, is that the same thing? Huh?
Yeah.
Okay, well, I thought some of you would think that, so I brought this along. Now, here I have 12 objects. All right, now I could regroup them just like the sticks. I could divide by 12, by 6, 4, 3, 2, 1. Now, are you telling me that the only way I can divide by 1/2 is to cut each one of these cute little sheep into 2 pieces and put it into one pile?
Oh, you are thick, Frank, really thick.
Well, I agree. Nobody would do that, right? No shepherd would even think of it, so there must be another solution.
Well, I just don't think that 24 halves in one pile means exactly the same as 12 divided into half pile.
Well, how are they different?
I don't know. Let me think about it for a minute. Maybe I can tell you later.
Okay, but the problem still remains. If the shepherd wanted to divide his sheep by 1/3, does that mean he would have to cut each one of these cuddly little sheep into 3 pieces?
Well, why would he want to divide sheep by 1/3 anyway? What question does this answer?
That's a good question. Who knows?
Well, how's this? How about if I put 12 of my sheep in a pen, and the pen is then 1/3 full? How many more sheep would it take to fill up the pen?
How about that, gang? Is that a division problem?
Yeah.
In a way.
Well, if you divide 12 by 1/3, that's 36. I guess that's right.
But you don't have to divide by 1/3. You can get the same answer by multiplying 3.
So are you telling me that dividing by 1/3 is the same thing as multiplying by 3?
Sure, at least in this case.
Dividing by 1/3 is the same thing as multiplying by 3?
She's right. Here, let me show you. 12 divided by 4 is 3. 12 divided by 3 is 4. Now, you will notice as the divisor gets smaller, the quotient, that's the answer, gets larger, all right? So this should be true whether we're dealing with whole numbers or with fractions. So 12 divided by 1/2, you would expect the answer in this box to be larger than 12.
Well, then Bill's right by saying that 12 contains 24 halves is not quite the same thing as 12 things in half a pile.
I'm sorry. I just can't think in half or third piles.
Well, nobody can, Bill, but here is how it works mathematically. 12 divided by 1/3 gives you the same answer as 12 times 3 over 1. You see, 3 is just 1/3 turned upside down.
Well, how does that work?
Well, let's look at it as a compound fraction first, okay? 12 divided by 1/3 is the same as 24 divided by 2/3 as...
Oh, a fraction family.
That's right. To start with, it is. There is a very special relationship between these numbers. 12 divided by 1/3. A very special rate is established between them. Now, that rate must be maintained at all costs. Whatever you do to one of these numbers, you must also do to the other number in order to make it come out even.
Oh, I get it. What we really did then was multiply both the 12 and the 1/3 by 30.
That's right. That's exactly right. Now, suppose you had 12 divided by 2/3.
Well, then you'd have to multiply 2/3 by 3 over 2.
Well, how do you know it's 3 over 2?
I don't. I was just following the pattern you used before, where you reversed 1/3 to 3 over 1.
That's very good, very good. But let me see if I can explain before Todd asks why. What you are doing here is finding the reciprocal. Now, the reciprocal is the number that you multiply a number by in order to get 1.
Oh, so the reciprocal of 2/3 is 3 over 2.
That's exactly right. Exactly right.
That explains it. The receptacle, the reciprocal.
Right.
The reciprocal.
Come up here and show it.
Oh, okay. I think I got an idea here. 12 divided by 2/3. That's the same as 12 over 1 divided by 2/3. Now, you want to make the denominator 1 to simplify the fraction, and the way you can do that is by multiplying this 2/3 by its reciprocal and by 3 over 2. But if you do that, you have to do the same thing to the numerator. So you'll do that up there. Now, this down here comes out 1. They cancel out because they're reciprocals. And what we've ended up with is we've inverted the divisor and we multiplied, which is, you know, that, so it kind of explains that rule. Let me see, you work it out. 3 times 12, that's 36, divided by 2 times 1, that's 2, equals 18. Yeah, that's the same thing Frank got, the way he worked. And, you know, this really kind of simplifies something about those partial piles, because what you do is multiply the 2/3 of a pile by its reciprocal to turn it into a whole pile.
That's right.
And
That's right. Good. That's terrific. Hang on to that discovery, okay? Because next week we're going to be working with decimal fractions, and we have to divide them, too.
Do they work the same way?
Well, it's a variation on the same theme. But that's enough poking and probing around at numbers for this week, okay? Let's take a break.
Okay.
We haven't even
Break.
butchered any sheep either.
Okay, here are a couple of things you should have gotten from this section of the program. 12 over 1 divided by 1/2 can ask, how many halves are there in 12? It can also ask, what would this relationship of numbers be if I were dividing by 1? The rule for division of fractions, which says invert the divisor and multiply, is a shortcut. What you are actually doing is multiplying the dividend and the divisor by the reciprocal of the divisor. Remember that the reciprocal is that number you multiply another number by to get 1. In this part of the program, we always divided a whole number by a fraction. The same principles apply if both of the numbers are fractions. Well, that's all for today. See you next time.
Local funding for GED on TV has been provided through a grant from the employees of DLH Industries, manufacturers of fluid, air, and vacuum delivery systems for the automotive industry. DLH, committed to excellence in manufacturing and broadcasting.